Hi, my name is Vincent Nellis, and in this video I'm going to show you how we use the tools, one of the tools developed in the P-Socrates project to do the timing analysis of an application. And for the video I'm going to use an application that we call the Wavefront application. So the first step and the first thing I'm going to do in this video is to explain you what is this Wavefront application. The Wavefront application starts by generating an image, and the size of the image is a parameter of the application. So in this example I set dim to 15, which means the application will generate a picture of 15 by 15 pixels. The application processes each pixel one by one, but each time it processes a pixel, in order to do this process, it needs the information about the pixel located directly on the top left, and on the left of the pixel that it is processing. This is why the application starts by processing the pixel on the top left corner. Then it processes the two pixels directly on the right and at the bottom of that first pixel. And then it moves on with the 3 pixels that are shown on the screen. Then it moves on with the 4 next pixels. And it does so until reaching the pixel on the bottom right of the picture. So that's why we call the application Wavefront, because the pixels are processed kind of like a wave. It is easy to see that we can easily parallelize this application. And this is another parameter that we can set in the source code of the application, which is the parameter n. N gives the number of tasks, of OpenMP tasks that we will create in order to process the image. So if we set n to 3, the application will create 9 OpenMP tasks, each of which will process a different part of the image, exactly as illustrated on this slide. If we set n to 5, this is the division of the image that we obtain. In this case, we will have 25 tasks, each one processing 3 times 3 pixels. But for the rest of the presentation, let's go back to the case of having n set to 3, and so we have 9 tasks. The first task, let's call it the first task, the one on the top left corner, does not have any dependency with other tasks, because that task is able to process its 15 pixels without requiring any information from the other task. However, the second task, let's call it the second task, this one, it will have a dependency with the first one, because when this task will process the pixel on its first column, it will need the information about the pixels on the last column of the first task. So this second task can only execute after the first task has completed. This is the dependency between the two tasks. In fact, every task that processes a part of the image which is in the first row of this division into tasks will have a dependency with the task directly on its left. The third task, or let's call this one the third task, has as well a dependency with the first task, because in order to process the pixel on its first row, it requires the information of the pixel on the last row of the first task, and that's why there is a dependency between this third task and the first one. Similar to the previous case, every task that processes an area which is located in the first column in these divisions of the image will have a dependency with the task directly on top of it. Now for this task, or any task which are not located in the first row or in the first column, those tasks will have a dependency with the task on the top because of the need of processing those pixels that depends on those pixels, and thus there is a dependency with the task on the top. And for these pixels, they have a dependency with these pixels, and then there is a dependency with the task on the left. But the pixel right here in the top left corner of this task has a dependency with the pixel on the bottom right of the task on the top left. So there is this dependency as well. In fact, when we will generate the TDG, the task dependency graph, we will have, for example, for divisions of the image into 3 times 3 tasks, we will have a TDG like the one we can see on the left, where the task 61 is the one on the top left corner, and the task 184 is the task on the bottom right corner of the image. The numbers here are given by the compiler, and I will not repeat here how the compiler does to compute those numbers. If we set n equal to 5, then we will have a TDG similar to the one depicted on the right hand side of the picture, where the task 151, the first node of this TDG, is the task processing the top left part of the picture. Let's have a look at the code now. This is the code source of the Wavefront application. The first function is to initialize the image. The image is this variable square, and we initialize every pixel by setting it to 1. Then we have this function sequential, which is the function that will be executed by every task. This function processes every pixel in a given area of the image. Then we have this Wavefront function where we create all the tasks, so the master thread creates all the tasks for every region of the image. Then we have the main where we just offload the Wavefront function. So now let's look at what we have to add to this code in order to perform the timing analysis. So first of all, we have to include this header file in this timing.h. In this file there are a lot of functions defined, and now we will have to instrument the code with some calls to those functions. First, we have to call this timing start of OpenMP declare target. Then we have to insert this call before the OpenMP parallel, this call at the beginning of the OpenMP master, this call at the end of the master. Here we give a name to the offload. Okay, so the entire offload, this is kind of the name of the TDG. This is a call that we have to insert at the end of the OpenMP parallel. And then this call that we have to insert after the OpenMP parallel. So that's it. That's a few calls that we have to insert into the code that we want to analyze. And finally, I'm going to add one thing more, which is a for loop here, because for the timing analysis we need a lot of data, and by executing this function only once we don't have enough data to process. So I'm going to iterate and perform this offloading over and over again until I get sufficient number of data. So this is a parameter that I will give to the program on compiling it. And I just close it here. That's it. I'm going to show you now how to perform the timing analysis. So this is the interface that we have created using our tools to perform the timing analysis of the Wavefront application. So in this variables tab, I have defined a certain number of variables, including, for example, the number of runs, which is this variable n-iter given to the program, telling the program how many times I have to do the offloading. There are many variables defined here. I will not explain them in details. You have the host, the IP, the port, lots of things. Then here you have all the comments. So there are quite a few comments here. The yellow ones are those that I executed on my local computer. The green ones are the SFTP commands. The blue ones are the one executed remotely through SSH. Then the pink one are the R scripts, and these dark blue ones are the Python scripts. And then the orange ones are the control commands that will change the value of the variables defined in that tab. Then I have defined a lot of actions, and these I will go in details now. So the timing analysis for dynamic scheduling, it works like this. We compile the source code of the application. This is the first step. And we run this application by assigning all the OpenMP tasks to the same thread. So on every cluster, for every offload, all the OpenMP tasks are assigned to the same thread, which means they are all executed sequentially on the same core. While they are being executed on this thread 0, on core 0, the 15 other cores, each one runs another thread, and those 15 other threads are producing as much interference as they can. So those 15 other cores, they execute kind of a virus, a tiny program which saturates the network and the access to the shared memory. All the OpenMP tasks, they execute sequentially while the other cores are creating this interference, and we measure the execution time of every task. And then we run the Wavefront application a certain number of time that I will set to number of run. I will set it to 10. Let's run it 10 times. And we will extract, so that's the first step, we will extract the MEET, which is the worst case execution time in a contention scenario. And we will check if it's schedulable or not. If it is schedulable, then everything's fine. If it is not schedulable, there is nothing much we can do, because this works because we have no clue with a dynamic scheduler in which order or on which core the task will execute. So we don't know what can be the maximum interference that they can incur, so we have to assume the maximum one. And the maximum interference is given in that scenario where they are all executed on the same core and we produce as much interference as we can. So this is the first step here, dynamic A1 compile. So as you can see here, you have all the steps of the dynamic timing analysis. The first one is to compile and extract the TDG. Okay, so if you click on the I icon here, you see the set of commands that are being executed by this action, and it will, as the name implies, it will compile and extract the TDG from the program. So the source code is in this folder source. In this folder interface, I have the XML file, I'm using this one, the XML file of the interface I'm using here with a set of actions, command, and variables. And by clicking this compile and extract the TDG, you will have a new folder with the results of this analysis here. So I'm going to click here. As you can see, it's compile and extract for dynamic. So I click, and all these commands are being executed right now. Okay, it's done. So now I have this folder dynamic that has been created, in which I have this extract TDG. I think finally is probably empty right now. Extract TDG, in which I have the TDG of my Wavefront application. So here I don't remember the parameters that I set. I'm going to check in the source code square.h. I have set the parameter n to 5. So I have 25 tasks. Yeah. Okay, the next step is to extract the MEET and check the schedulability. So I click. Now it runs the program 10 times. Okay, done. Okay, it's over. And now if I go back to my dynamic folder, I have this extract MEET step, in which I have the ETDG, so it's the extended TDG, where I can see now every node has been annotated with the maximum execution time in contention, which is given in microseconds here. Here I can see the mapping that has been created. It's a dynamic mapping, so for the 25 task, or the map field has been set to -1. What else do I have? I have the task observed execution time, so these are the 25 tasks, and for each one I will have the execution time that has been observed in the 10 runs. So I have run the application 10 times. This is the overhead, and this is the execution time in microseconds of each task for each run. So this folder extract MEET contains all the files that have been created during that experiment. Now I can extract the MAIT, which is in this mode I will not assign all the tasks to the same threads. I will dynamically schedule all the OpenMP tasks on the 16 cores of the first cluster, and I will measure their execution time. So here I'm not trying to enforce a particular scenario. I'm not trying to enforce isolation or to enforce an extreme contention scenario. Here I'm just running the application 10 times again, and I measure the execution time of every task. So I click here. We can have a brief look at the action once it is over, so that we see in details what it does. This one, I click on the eye, so it creates some folders on my laptop. It connects to the machine. It recompiles Erika in dynamic mode to make sure that we are using the dynamic scheduler. Then it creates and cleans some folder on the MPPA. It uploads the source code, it compiles it, create the TDG, then it generates the dynamic mapping, this mapping file, the mapping.c file. Then it downloads the mapping to my folder. Then it compiles the source code for the IO application, for the cluster application. It creates the multi-binary. It runs the multi-binary. Then it downloads the output files, the power traces, and then these set of steps here, it extracts from the output, it extracts the execution time of every task, it applies the extreme value theory to the task execution times. This is an optional step. Actually, it's done here, but I'm not taking the results of this step into account in the rest of the process. However, I could if I wanted to, but in this demo we are not using the results of the extreme value theory. Then we annotate the TDG with this MAIT, this maximum actual execution time observed, and we upload this annotated TDG again, and we check this time we check the schedulability for the dynamic scheduler using this new observation, this maximum actual execution times, and we download the results of this schedulability analysis, and then we close the connection. So here you can see all the files that have been created. If I go this time, there is a folder extract MAIT. We have the annotated TDG in the ETDG folder. Now we can see the MEET, but also the MAIT with the number of microseconds again. As we can see, it is much less than the execution time in an extreme contention scenario. What else do we have in this folder? We have the mapping. It's again everything set to -1 because we are using the dynamic scheduler. We have the execution time observed for all the tasks, the output, the power traces, and the results of the EVT here, but I will not explain this because we are not using them. Okay. And also in the final we have these results from the schedulability analysis. So we had those from the previous step, from the MEET. As we can see, so if we perform the schedulability analysis, assuming dynamic scheduling, and we assume this MEET as the execution time of every task, we get a response time for the entire TDG, a worst case response time of 34 milliseconds here. And because we set the deadline and the period of the TDG very high, then it is schedulable. As you can see, the analysis returns yes. And if I go to the schedulability analysis result for assuming the MAIT, the response time is much less, 68 microseconds, and it is also schedulable. Now in this next step, we are again running the application without enforcing any particular situation. We are not enforcing the isolation or generating the maximum interference. We are again, exactly like in the previous step, we are running the application normally, but here we will not measure the execution time of every individual task. We measure the end-to-end execution time of the offload. The process is roughly the same. The only difference in between all these steps are mainly there are the few comments that differ from one action to another here, but one of the big difference is the third comment. For example, here set mode to contention when I was extracting the MEET, or set mode to deployment task timing enabled when I'm extracting the MAIT, or set mode to deployment phase timing enabled when I'm extracting the end-to-end response time, because this step will change the value of some of the variables that I'm using in the tools, and those variables are used during the compilation process. And the difference when I will compile the code, the difference of having different values for these variables will have a very important impact on the timing.h, which is this library that I have added to that contains the definition of all of these functions. So these functions will behave differently depending on the value of some of these variables. For example, when I will set now in this extract the end-to-end response time, some of the variables will be set to on and some others will be set to off. And for example, this command here, this function here, timing begin of OpenMP master and timing end of OpenMP master, will record the end-to-end time to execute all these OpenMP tasks. However, in another mode, for example, when I was extracting the MEET, these functions were doing something different, but they were not measuring the end-to-end time. So these are the big differences between each of these actions. So I'm going to run this action here. Okay, and now in the dynamic I have extract response time, I have the mapping and the outputs. This is the worst case that has been observed, and the last step is to write a summary of all the results obtained in the previous step. So I'm going to execute this one. Done. It's a short one, and this one creates some files in this final folder. For example, you have the final ETDG, the one that has been annotated with MEET and the actual execution time. You have the result from the schedulability analysis for assuming the MAIT. You have the result assuming the MEET for the execution time of every task, and you have a task summary. And this file contains several columns. The first one is the ID of the TDG. Here there is only one offload, so there is only one TDG. You have the ID of every task, its MEET, its maximum execution time in contention, when all the tasks are executed sequentially on one core and the other cores are generating the maximum interference. Then here we have the maximum execution time observed when running the application normally, which is the MAIT. And here we have an increase, which is the ratio between the MEET and the MAIT, to see how much the task is impacted by some interference. Then I have created this action which executes the five actions that I just have shown. It executes the five actions sequentially. Then we have the static analysis. So the static timing analysis is when we perform timing analysis using a static scheduler. Here the methodology is very similar, but the process is a bit different. This is a picture of the methodology. So we start by, at the step 1, we start by compiling the source code into a multi-binary. And then, similar to the case of the dynamic scheduler, we extract the MEET, the maximum execution time in contention. The third step is to try to find a mapping, assuming that every task now runs for its MEET. The mapper will try to find a mapping that satisfies the deadline. And at the same time, it cooperates with this schedulability analysis to tell whether the given mapping meets the requirements. If the mapping, if all the timing requirements are met for the mapping that has been computed in step 3, assuming the MEET for every task, then we know it will always work at runtime and we can stop the process here. Because at runtime, when the application will be executed normally, the task will never take an execution time as high as the MEET. So the total response time will be lower than the one computed during the schedulability analysis. So we know that even if the upper bound computed at step 4 meets or satisfies all the timing requirements, then at runtime all the requirements will be satisfied as well. If the schedulability analysis returns no, then we extract the MIET, which is the maximum execution time in isolation. In this case, all the OpenMP tasks are, again, like at step 2, it's very similar to step 2, all the OpenMP tasks are executed sequentially on one core, on core 0, but this time all the other cores are kept idle. They don't produce any interference. That's what we call the isolation mode, because each time an OpenMP task runs, it does not incur any interference from the environment. So this is kind of the best worst case execution time we can get. And we again annotate the TDG. This time we try to again derive a mapping, but this time we assume the MIET as the execution time of every node, and we perform the schedulability analysis. If now the schedulability says that it is not schedulable, which means that we couldn't find a mapping which satisfies all the requirements, even assuming this MIET, then we know we will never find one, because again these MIET are the best worst case possible, which means that at runtime we will observe an execution time slightly higher. So even if the system is not schedulable assuming this MIET, it will for sure not be schedulable at runtime, where the response time will be a bit higher. If it is schedulable, assuming this lower upper bound, we have to now extract the MAIT, which are the execution time at runtime, and try to see if for that mapping, the one that was used at step 6, computed at step 6, if now the system it still satisfies all the requirements. So we extract the MAIT, so we run the application normally and we measure the execution time of every task. We annotate again the TDG and we check if it's schedulable. If it is, then we are good to go. The system can be deployed for that mapping. It will meet all the requirements. If it is not, then we produce a table which gives for every task its MIET, its MEET, its MAIT. So all these values that have been derived, or the mappings that have been derived, and all the task, or the co-scheduled tasks. So we will see for each task the set of tasks it has been executed with. Okay. And based on this, we will be able to put restrictions on the mappings. So if we see that one task has a huge execution time at runtime, close to its MEET, then we know that this task was executed together with another task that was creating a lot of interference. So we may want to add a restriction to the mapper and say now these two tasks have to be executed on the same core so that they cannot interfere with each other. And then we will iterate here until we find a functioning mapping, a mapping that satisfies all the requirements. But the final step, the final part of this loop has not been implemented yet. So we terminate the project, the process here when we generate this table. Now the next step that will be done in the next few months, I guess, will be to modify a bit the mapper so that we can inject restrictions. We can say I want this task to be scheduled with that one, or that task to never be scheduled together with that task on different cores, because otherwise they can interfere with each other. So this is the missing step right now. But everything has been implemented until the creation of this task. So that's one I'm going to show you now. So the first step here, we will compile and extract the TDG. So I run this. And this is very similar to the dynamic case. Now I have this static folder that has been created next to my dynamic folder, in which I have again the extract TDG, and I have the TDG of my application here. This one has not been annotated yet. Next step, as we can see, I can close this. Next step is to extract the MEET and to annotate the TDG. Try to find a mapping and try to find a schedulable mapping. So this is the next, these steps 2, 3, and 4. That's what we are going to do now, which is in this action, extract the MEET and check the schedulability. So I click here. Done. Now I have this extract MEET, and it is the same folder as the one for the dynamic case. Next step, I can extract the MIET. So here all the tasks are executed sequentially on the core 0, and the other cores are not creating any interference. They are kept idle, while in the previous case they were creating a lot of interference. Then I can extract the MAIT based on the mapping computed for the MIET, and we will check the schedulability. So this next action corresponds to so the first action was to extract the TDG. The second, I will show on the screen here, the second action was this. So this was the second action. The third action was to extract the MIET and find a mapping which is schedulable. And now the next action will be to extract the MAIT, annotate the graph, check the scalability, and derive this table. So I'm going to do it now. Done. Then the next one, it's not depicted on my slide, but we will extract the end-to-end response time. So this will measure the response time of the entire TDG rather than focusing on every individual OpenMP task. So I'm going to run it. And here the last one is to write this result summary. Done. So now I can see all the folders corresponding to each step. Extract the MIEET, the MIET, the MAET, extract the response time, extract TDG, and final. In this final, I have again this task summary, and here I have the index of the TDG, the index of the task, the MIET, so the worst case execution time in isolation, and then the MAIT, the maximum observed execution time. So as we can see, the maximum observed execution time is always equal or higher, for example 5 and 6, 4 and 6, than the execution time in isolation. Then we have the MEET, the maximum execution time observed in a contention scenario, an extreme contention scenario, which is much higher. Then we have the core to which the task has been assigned. So here we have a certain number of tasks assigned to core 0, some of them are assigned to core 1. And then we have the list of tasks every task is executed with on the same core. And the last parameter is the sensitivity. And the sensitivity is, so the MAIT is always between the MIET and the MEET. And we want to know how close it is to the MIET. So a sensitivity of 0% means that the execution time observed is equal or very close to the minimum the execution time in isolation. a sensitivity of 100% would mean that this maximum execution time observed is equal to the execution time in an extreme contention scenario. So this is really the table that will allow us to say, okay, this task has incurred, for example, if a task has a sensitivity of 50% here and here, then it means it will be good to execute these two tasks on the same core so that they cannot interfere with each other in the future. And that's the restriction that we want eventually to add to the mapper so that it can recreate a mapping where we don't observe this interference. And now to conclude this video, I'm going to show you that I have this function, this action run all, which runs all of the action related to static analysis, and then I have an action which is run all actions for dynamic and all actions for static. So I can show you now. I will delete the dynamic and the static folder, and I will set the number of variables equal to 20. This is the number of runs, so the number of offload that will be realized at every execution of the application. And now if I run everything, it will run in sequence these 299 comments, and it will perform the entire timing analysis of the application for the static scheduler and then for the dynamic one. And these are all the commands that execute in the background. It takes a bit of time. %. I'm not sure which step it is now. Done. And as you can see now, the dynamic folder and the static folder have been recreated, and you have all the information on the timing analysis here. For example, in the final you have this task summary. Yeah, it has been, I have opened quite a lot of files here. You have the ETDG, where every node has been, every task ID has been annotated with the MEET, the mapping to which core it has been mapped, the MIET, the MAET. So yeah, all the results are there. Thank you very much for watching the video. I hope it was helpful for you. Ciao.